In this video, we're going to use the first derivative to talk about increasing and decreasing. So remember that a function is increasing if it's going upward. If my function is generally going that direction, it's increasing. If my function is going downward, that direction, it's decreasing. So let's consider this graph. All right. What can we say about the tangent lines when the function is decreasing? All right, well, decreasing is this part of my graph. All right, so let's just pick a couple points and look at their tangent line. So I can pick a point here. The tangent line looks like that. I can pick a point, say there. The tangent line looks like this. Pick a point just before the decreasing part ends, and the tangent line looks like that. What do all those tangent lines have in common? Well, when we're talking about lines, it's not really much to talk about. It's really just like the intercept and the slope. These definitely don't have the same intercept, but you can see they all have a similar slope. They're all going downward, so their slope is negative. And if the slope is negative, that means our tangent line has a negative slope. Right? And our slope of our tangent lines is our derivative. So if the slopes are negative, the derivative is also negative. All right, so we know everything that's decreasing is going downward, which means all the tangent lines are going the same direction, which means their slopes are negative, which means the derivative is negative. All right, so here's that kind of wrapped up in a nice bow. If my function's decreasing, my derivative is negative. We didn't look at it, but also if you're going upward, all those are going to have positive slopes. So if my function is increasing, my derivative, the slopes of the tangent lines, are all positive. All right, so here's one big thing that you have to do for like calculus in general is figure out when when a function is increasing or when is it decreasing. All right, so again, if we think about the last slide, it's determining when the derivative is positive or negative. So we're gonna have to find the derivative first. Let's do that. All right, derivative is gonna be 2x minus 4. And how do you determine when a function is positive or negative? Well, you could graph it and look at the graph, but that tends to take a while. All right, for this one, it's a line, so actually it wouldn't be too bad. I've written in general, graphing a function just to determine positive or negative takes a little bit of time. So we need another method. And if you think about, if we were to graph it, I'd say this was the graph, it's not because it's a line. When we go from the positive y values to the negative y values, what do we have to do? We have to cross the x-axis, which is when it's equal to 0. So knowing the places where our function is equal to 0 is going to help us determine where these switches happen. So the first thing we actually need to do, take our derivative and set it equal to 0. Solve this. X equals 2. All right, so this is not the answer in any sense, but this helps me get the answer because if I make a number line, and I put 2 on it, 2 is the only place my graph can possibly switch from positive to negative. Because 2 when it's equal to 0. All right, so let's just say like this was 2 right here. So a couple different things can happen. It can do it like that and stay positive on both sides. It could go like this and stay negative on both sides. But it could also switch from positive to negative or negative to positive. So those are like all the possible things. But the important thing is it's not going to switch over here because I had to get 0, and it's not where 0 is. It only happens at 2. So I use this 2 to my advantage. What I'm going to do is think about to the left of 2, what are some numbers to the left of 2? 0's to the left of 2. So what happens at 0 for my derivative? I'm going to plug in 0 into my derivative. Oops, that's a 0. And I get negative 4. So since when I plug in 0, I get a negative, everything else in this region has to be negative because I can't switch the positives until I get to 2 and I can cross the x-axis. What's the number to the right of 2? This is 2, 3 because it's just to the right of 2. If I plug that in, again, I'm plugging into my derivative because the whole thing is I want to know if my derivative is positive or negative. 2 times 3 minus 4, 6 minus 4, that's 2. And I don't care about the actual value, I just care about the fact that it's positive. And since 3 is positive, everything else in this region has to be positive. All right, so for my original function, all right, I know the derivative is positive and negative now, so my original function in this region has to be decreasing, and this region has to be increasing. And to answer the question, I want to know when it's increasing from 2 to infinity. All right, so this would be the final answer for this problem. It switches at 2, and then after that, it's increasing forever. All right, here's the graph of that function we just worked with, x squared minus 4x. All right, does it match with our findings? Well, x equals 2 is here. And you see at 2, that's where the turn happens, and everything after that, my graph is going upward and increasing. So it's good that the math that we did on the last slide matches what the graph is telling us. All right, so here's a general strategy. Again, sometimes when these are written down in steps, it's actually more confusing, but here's some steps you can kind of think about when you're doing that. If we want to find out when a function's increasing or decreasing, we need to find the derivative. All right, so the first thing is find the derivative of that function. All right, then we find the critical points, because at the zeros, we can switch from positive to negative. Also at undefined points, we can switch from positive to negative. So I have like an asymptote or a jump or something you can switch. All right, so we have to find all the critical points, not just equal to 0, but the critical points. All right, we're going to create a number line. All right, the number line is going to help us keep track of all those places we can switch. In the number line, we pick a test point in each of those regions, and we plug that test point into the derivative. So this is something where we're making these number lines a lot, and you got to figure out where you're actually plugging in your test point. And in this case, we're plugging into the derivative because we want to know if that is positive or negative. And then at the end, we interpret our answer based on our number line. All right, so let's do another example. All right, we have this function g of x, and we have to find the derivative first. We have to find the critical point, so there's two things. We have to figure out when it does not exist and when our derivative is equal to 0. Luckily, our derivative is a polynomial, so it's never going to not exist, so we don't have to worry about that. We just figure out when it's equal to 0. Now we can factor this one, and we get 2 answers. All right, so again, these are the critical points. These are the places, the only places my derivative can switch from positive to negative. All right, so I'm going to make a number line. I'm going to make sure I put them in order, so not 3, -1, because -1 happens to the left of 3. I'm going to pick a test point in each region, so something to the left of -1. Generally, just keep the number small. Between -1 and 3, if you can pick 0, always pick 0, because it's easy to plug in. To the right of 3, say 5. And again, I'm trying to figure out if my derivative is positive or negative. So all of these values I'm plugging into my derivative function. So I plug in -2. Four plus 4 minus 3 is 5. So when I plug in -2, I get a positive value. So everything else in this region has to be positive. 0 is so nice. If I plug in 0, I know I'm going to get -3. All the x's go away. And since I got -3, everything else in this region has to be negative. And I say 5. I'm going to get 5 squared minus 2 times 5 minus 3. 25 minus 13 is 12. And the actual value doesn't make or matter too much. I just care that it's positive. So as long as you're doing it accurately enough to determine positive or negative, everything else in this region is positive. So now I know my derivative is negative to the left of -1, or sorry, positive to the left of -1, negative between -1 and 3, and positive after 3. Right. And now I can finally answer my question, when is my function decreasing? My original function is decreasing when my derivative is negative, so my answer is -1 to 3. If I was asking when your function was increasing, it's when your derivative is positive, so you get these 2 different intervals for your answer. All right, so here's one for you to try on your own. All right, determine when this function is increasing. All right, I'll show you the answer in 3, 2, 1. And the answer I end up getting is 1/4 to infinity. So I take the derivative, set it equal to 0, and figure out when it does not exist. But again, that doesn't happen because it's a polynomial. So I set it equal to 0. I get the only place my derivative can change sign is at 1/4. Do my test points, figure out where it's positive or negative, and then from there interpret. I want it to be increasing, so I'm looking when the derivative is positive, which is after 1/4. All right, so here are the important points from this lesson. If the derivative is positive, the original function is increasing. If the derivative is negative, the original function is decreasing. Okay? And you can use a number line to determine these intervals for an expression. And we're going to do this number line thing for a lot of different scenarios, so it's just something you have to get used to. Figuring out when you could switch signs, which is 0 or undefined, and then picking those test points in the different intervals it creates.